Hello students. In this lesson, we are going to study about addition to carbon-carbon multiple bonds. In content, here, we will cover addition to cyclopropane ring, hydrogenation of alkynes, hydrogenation of aromatic rings, and ENE reaction. Additions to cyclopropane ring. Cyclopropane has a triangular planar structure, due to which the bond angles between carbon-carbon bonds are expected to be 60 degrees. This is far less than the thermodynamically stable angle of 109.5 degrees as per the sp3 hybridization of the carbon atoms. Due to this, there is a considerable amount of ring strain in the cyclopropane molecule. In addition to this angular strain, cyclopropane also suffers additional torsional strain. The torsional strain is due to the coplanar arrangement of the carbon atoms, wherein leading to the eclipsed arrangement of the carbon-hydrogen bonds. It has been suggested that significant rehybridization occurs in cyclopropane, and bonding between the carbon centers occurs in terms of bent bonds, according to Coulson-Moffett model, wherein the carbon-carbon bonds are bent towards outwards, so that the interorbital angle is 104 degrees, which consequently reduces the level of bond strain. So it is intermediate between sigma and pi bonding. These bonds are also sometimes called banana bonds, as you can see in the figure shown here. Thus, the CC bonds have more P character than normal, while CH bonds have more S character. Thus, it can be seen that ring strain substantially weakens the CC bonds of the cyclopropane ring. Hence, cyclopropane is much more reactive than alkanes or other higher ring systems. So you can see here, in the Coulson-Moffett model, that although the internuclear angle is 60 degrees, but because of the banana bonds, the orbital R went towards outsides, so that the interorbital angles is around 105 degrees, and because of that, the strain is slightly reduced, but there is still considerable strain. That is why it undergoing addition reaction to release the strain. From the preceding discussion, it becomes clear that cyclopropane ring system suffers from a large ring strain, which is a combination of angle strain and torsional strain, which leads to a significant weakening of the CC bond. Thus, CC bonds show a greater P character, while CH bonds have more S character. Thus, in effect, the cyclopropane ring undergoes any such reaction, which can subsequently help in relieving the ring strain. Most of these reactions are similar to those of alkenes, and most common of these are addition reactions, electrophilic, nucleophilic, or free radical, which lead to opening of the ring. Here, CC bond is broken, leading to ring fission, and the atoms of the reagent attach at two terminals of the resulting propane chain. Depending upon the substitution of cyclopropane ring, which can be electron donors or acceptors, any of its three bonds are likely to undergo cleavage. The reagent must be able to polarize itself into nucleophilic, and electrophilic centers, for the subsequent addition to occur. This is as shown in the following figure. Thus, propylene reacts more readily with Br2 or Cl2, while for reaction with cyclopropane, a Lewis acid is required, that is FeCl3 or AlCl3, to effect sufficient polarization of the Cl2 or Br2 molecule. Because being nonpolar, it will not be able to polarize, so you have to give the polarization to the reagent molecule, and that's how reaction will be happen. So as shown here, X- and Y+ are the reagent adding, and Y+ attack on first carbon, and followed by X- on the third carbon, to get the 1,3 addition product. Electrophilic addition to cyclopropane. The electrophilic addition, in substituted cyclopropanes, generally follows Markovnikov's rule, wherein hydrogen adds to the carbon, which already contains more hydrogens. That is as shown here. If you have a substituted cyclopropane, where one carbon is having one methyl group, and other carbon contain 2 methyl substituent, and if you are adding HBr, then out of these 2 carbon, hydrogen will go to less substituent carbon, and you get this product. This suggests that the mechanism comprises of an initial attack by the electrophile, that is, H+, on the ring carbon with the most hydrogens, generating a positive charge on the carbocation. This positive charge may be transferred onto the other carbons of the ring. The most favorable intermediate would be the one in which the positive charge is on the most substituted carbon. Most stable carbocation is subsequently trapped by its reaction with the nucleophile, as shown below. You are starting with cyclopropane, where this particular carbon has alkyl substituent. So, when it attack by H+, you will get this carbocation. Then X- will attacking to that position, where it is the most stable carbocation. Nucleophilic addition to cyclopropane. Ring fission of cyclopropane by nucleophiles is possible only when an electron withdrawing group, W, is present on the ring. So, the electron withdrawing group will make the cyclopropane ring to have electron deficiency. That is how this nucleophile can attack at this second position carbon with respect to the W group. And as it attacks here, there will be cleavage of CC bond of cyclopropane, and you get the carbanion, which later attack by H+. Eventually you have the nucleophilic addition is happening. This reaction has been used widely in organic synthesis, and can be used as a homologous variant to secondary amines or alcohols through opening of the cyclopropane ring. This reaction has been used widely in organic synthesis, and can be used as a homologous variant to a Michael type addition to generate a 5-membered ring, as shown. There is a cyclopropane attached to 2 esters, and both the ester group will be helping in nucleophilic addition, as they are electron withdrawing groups. When this treated with diethyl malonate, this methylene group, that is CH2 in between, in presence of base, will be attacking as a nucleophile, to this particular carbon. Then the bond breaks, and there will be formation of carbanion. Once we'll get this carbanion, there can be another attack, because now this will attack as nucleophile, and these carbon will be electron deficient, thereby you will get this alkoxide ion. In these alkoxide ion, it will going out as a good leaving group, giving you this particular keto, and furthermore, in the presence of basic medium, another carbonium is generated, because CH2 in between these two electron withdrawing, CO, and COET. Further, when you work up with proton, will give you this particular product. So you can see the C- will make this OH- as a good leaving group, so ethoxide ion goes out, and as a result, keto group arising here, ketoester, which is 5-membered ring, having 3 ester substituent, and 1 keto. And because the medium is basic, there may be further generation of this carbanion. Finally, when work up with acid, it will give you the final 5-membered product. Addition of free radicals to cyclopropane. Free radicals can also add to the cyclopropane ring system easily. For example, Br2 can add to a cyclopropane ring in presence of UV light via a free radical mechanism. So in this mechanism, initially, Br free radical, which is formed with the help of UV light and bromine, the Br dot will attacks the least hindered carbon to yield the most stable radical, and this free radical will be taking another Br dot from bromine molecule, and another Br dot will be generated, and you will get the addition product. The Br dot in turn will attacking the more and more cyclopropane molecule. Like you are familiar with the chain initiation, chain propagation, chain termination, so here also, that and be applied. And the second one goes to the most substituted carbon. Hydrogenation of alkynes. Alkynes are catalytically hydrogenated to alkene, and further to alkane, in a stepwise manner, as discussed earlier. Both alkene and alkane may be isolated. For complete conversion of alkyne to alkane, platinum, palladium catalysts or raney-nickel are used. However, if a propargylic alcohol group is present, it may occasionally undergo hydrogenolysis, especially when PT catalysts are used. As mentioned earlier, it is possible to partially hydrogenate alkynes to alkenes by the use of catalyst poisons. The use of Lindlar's catalyst to get Z-alkenes is a most important example of such transformation. More electrophilic alkynes absorb more strongly on the electron-rich catalyst surface than the corresponding alkenes, aids such partial hydrogenations. However, when using Lindlar's catalyst, it is important to prevent overhydrogenation by carefully monitoring the reaction conditions and limiting the hydrogen consumption to around 1 mole. Such selective hydrogenation to Z-alkenes has found significant use in the synthesis of natural products and some pharmaceutically important intermediate. Hydrogenation of aromatic rings. Aromatic rings are among the hardest to be hydrogenated, and even with precious metal catalysts, require higher temperatures and pressures. But, once a benzene ring starts to hydrogenate, there is nothing like partial hydrogenation, and it hydrogenates to cyclohexane. This is because, when benzene has been converted to cyclohexadiene, it is associated with the loss of resonance energy, and the subsequent hydrogenations are exothermic and faster than the first one. PT and RH catalysts are common and used at ordinary temperatures, whereas Raney nickel or Ru catalysts require higher temperatures and pressures. Raney nickel is used for large-scale hydrogenations involving heating at 150 Celsius, at high pressures, 100 to 200 atmosphere. RH over alumina is another prominent catalyst, which requires milder conditions than others. Also, it does not cause hydrogenolysis of the sensitive CO bonds present in the molecule. Hydrogenation of polycyclic aromatic rings, such as naphthalenes and phenanthrenes, are also performed, and by varying the reaction conditions, partially hydrogenated or fully hydrogenated products may be obtained. For example, Raney nickel may be used to obtain tetrahydro or decahydronaphthalene by varying the reaction conditions. Similarly, 9,10-dihydrophenathrenes or anthracenes can be obtained by reduction over copper chromite, and to fully reduce them, more active catalysts are required. ENE reaction. The reaction between an alkene which has an allylic hydrogen, known as the ENE, with the compound, conjugating a multiple bond, that is, the enophile, is known as ENE reaction. The other terminology for this type of reaction is Alder-ENE reaction. The ENE reaction was first recognized and systematically studied by Alder. They resemble 1. 5-sigma-tropic rearrangement, since a sigma bond moves, and they also resemble cycloaddition, like Diels-Alder reaction, with one of the pi bond of the diene being replaced by a sigma bond. Since the reaction is bimolecular, and no ring is formed, they are neither sigmatropic shifts nor cycloaddition reactions. Electron withdrawing groups on the enophile and electron donating groups on the ENE favor the reaction. Lewis acid catalyst, such as AlCl3, has also been shown to lead to rate enhancement for ENE reactions. The Lewis acid catalyzed reactions afford high yields and selectivity at lower temperatures, making the ENE reaction a useful C-C bond forming tool for the production of intricate molecules and natural products. In general, in ENE reactions, a hydrogen atom moves from the ENE component to the enophile, but other atoms can also move equally well in principle. Practically, other than hydrogen, ENE reaction are found to have metal atoms, like magnesium, nickel, palladium, lithium, boron, aluminium, zinc, platinum, in place of hydrogen atom. Such reactions are called a metal-ENE reaction. The substrate may also have one or more heteroatoms in place of carbons. Thus if the atom carrying the hydrogen is an oxygen atom, and the atom to which it is moving is also an oxygen atom, it becomes an aldol reaction. The 4-electron system, including an alkene pi bond and an allylic CH sigma bond, can participate in ENE reaction, in which new CH and CC sigma bonds are formed. In order to form a new sigma bond, there is a migration of ENE double bond and 1,5 hydrogen shift. And the product is a substituted alkene, with the double bond shifted to the allylic position. Activation barriers decreases along the enophiles in the following order. Mechanism. The main frontier orbital interaction occurring in an ENE reaction is between the HOMO of the ENE and the LUMO of the enophile. The HOMO of the ENE results from the combination of the pi bonding orbital in the vinyl moiety and the CH bonding orbital form the allylic hydrogen. However, if the enophile becomes more polar, its LUMO has a larger amplitude on carbon, yielding a better CC overlap. Thank you.